In this lesson, we'll examine our place in time. Given the expansion rate of our universe today, scientists estimate that our universe is about 13.8 billion years old. Well, back near the beginning, the entire universe was in a volume of space smaller than an atom. And then something amazing happened. It began to expand rapidly. In the earliest moments of the universe consisted of just a hot, dense fog of energy. But the universe was expanding, and the average temperature of the universe was cooling. Now, Professor Einstein helped us understand that energy and matter are two sides of the same coin. Energy can be transformed into matter and vice versa. So as the universe expanded and cooled, particles began to so-called freeze out of the energy. Energy transformed into particles of matter. Here we see three such particles, the very building blocks of atoms: electrons, neutrons, and protons. As well, there was lots of light buzzing around, lots of photons of light of various wavelengths. Now, these particles would have been smashing around with such intensity, such energy, that atoms could not yet form at this early stage. Rather, at this early stage, another process was occurring called nuclear fusion. And this is the kind of process that happens in stars today. But at this early stage of the universe, protons, which are just the nuclei of hydrogen atoms, protons were smashing into other protons and neutrons, and new combinations of particles formed. Now, when protons and neutrons collide, they can stick together, and this is the strong nuclear force that can hold some of these particles together. And you can get a situation where the collisions of some of these particles can form the nuclei of the next heaviest element, helium. So here at this stage of the universe, then, we have the nuclei of hydrogen and helium. And the helium emerged from the fusion of hydrogen nuclei. And all of what you see here so far was happening in the first 3 minutes after the Big Bang. A few 100,000 years later, atoms begin to form. As the universe expanded and cooled, the particles were moving around with less energy, and this allowed the nuclei, like the hydrogen nucleus, a proton, or the helium nucleus, to capture electrons. Here we see the hydrogen atom, 1 proton and 1 electron, and the helium atom, 2 protons and 2 electrons. And recall the 2 neutrons there holding the nucleus together. So now we have a universe filled with the 2 lightest elements, hydrogen atoms and helium atoms. In addition, we've seen the operation of 2 forces in nature. The strong nuclear force keeping the nuclei, for example, of the helium nucleus together. And we have the electromagnetic force keeping electrons bound to the nucleus of the atom. Well, now it's time for gravity to make an entrance on the universal stage. So at this point in the universe, we have giant clouds of hydrogen and helium gas. Now, all objects with mass feel an attractive force with other objects with mass. That's the gravitational force. So what will tend to happen is that gravity will tend to compress these giant clouds. These giant clouds would be future galaxies composed of billions and billions of stars. Scientists sometimes call this the dark era. So we have the formation of atoms, but stars had not yet formed. A few 100 million years after the Big Bang, we get the first stars. So the compression of clouds of hydrogen and helium form stars. Gravity will compress the cloud of gas to such a high temperature and pressure that nuclear fusion occurs in the core of the star, fusing 4 hydrogen nuclei to form a helium nucleus, and that releases energy. So stars emit light because the surface of the star is very hot, and hot objects glow. They emit light. Why is the surface hot? Because nuclear fusion is happening in the core of the star, and that releases energy. So at this stage then, there were these giant clouds of hydrogen and helium gas, and we have local clusters, local compressed clouds, which would be the first generation of stars. But we would not have any heavy elements mixed in the hydrogen gas, because it's going to be the stars that will have to forge those heavy elements. Neither are we going to have rocky planets, because rocky planets are made of heavy elements. We could have gas planets like Saturn and Jupiter, which are made of hydrogen and helium. So at this early stage, the only kinds of planets that could have existed would be the gas planets. There would be no heavy elements yet produced by the universe. Now, as stars ran out of hydrogen, they could fuse helium into yet heavier elements like carbon. So the cores of stars are element factories, forging heavier and heavier elements on the periodic table. When a star runs out of all nuclear fuel, if it's massive enough, it can explode in a supernova. And so now, in the next phase of the universe, we've got the first generation of stars, some of which have gone supernova, and they're going to blast the heavy elements back out into space to mix with the remaining hydrogen in a galaxy. In addition, the explosion itself creates even heavier elements on the periodic table. So at this stage then, we start to have the formation of enriched nebula, clouds of gas and space dust, and the space dust are the very heavy elements ejected by the supernova. And as these heavy elements blasted out into space, they would interact and collide and form small molecules of different types. As more and more supernova ejected heavy elements out into space to mix with the surrounding hydrogen gas, we now have enriched nebula. We have hydrogen gas to form new stars, and we have the space dust, the heavy elements, the small molecules, the bits of particles of rock and metal and ice that can form rocky planets. And we know about 10 billion years after the Big Bang, or 4 billion years ago, one of those rocky planets produced life. So we can summarize the history of the universe with this chart. 13.8 billion years ago, the Big Bang, an expanding region of high-density energy, transformed into subatomic particles, which combined into hydrogen and helium atoms, compressed by gravity to form stars. And it was nuclear fusion that produced heavy elements, which were ejected into space by supernova, which added these heavy elements to nebula. And nebula can form new solar systems with rocky planets in habitable zones, which provided conditions for complex organic chemistry, ultimately producing life on one rocky world, our home, planet Earth. So the story can be summarized as the early universe had energy, which transformed into the nuclei of these two simplest elements on our periodic table. And then stars made all the rest of the elements on the periodic table. And then those atoms can combine into molecules, and some of these molecules assembled into living cells. What we have is new and more complex things emerging over time. And it's the laws of nature that govern this process. So this is our history, our place in space, and our position in time. But while it's our history, it's also the history of every other life form in the galaxy, if there are other life forms in the galaxy. If we could communicate with these intelligent aliens, we would have much in common. What we would have in common is history class, the history of the universe that produced us and them.